GM everybody, hello, hey, I'm Yasin, and today we're kicking off another day full of workshops. Kicking off with a really exciting one with Justin Drake on the native rollup. I have another one later on today, but on that in a bit. Let me quickly get Justin on stage as we begin the workshop. Justin, you should be seeing a pop-up on your end. Everybody do sound off in chat, say hi, make sure to make some noise, make sure that Justin feels very welcome, and as always, make sure to post your questions in the questions tab as Justin will be replying accordingly. Hey, Justin.
Hello. Can you hear me okay?
Yes.
Perfect. So am I good to get started?
Yeah, feel free to share your screen and take it away.
Okay, perfect. Okay, so today I've only prepared 2 slides. This first slide here is to try and zoom out and provide a little bit of context on what the topic of today's discussion is. So if you consider the world computer, really it provides multiple services. There's multiple layers to the stack, if you will. So one of the services that the world computer provides is settlement. So basically when you post your state roots on chain, then you have direct native access to hundreds of billions of dollars of TVL. And if you are settled on Ethereum, I say that you're an L2. That's my definition of L2. And then another layer of the stack is data availability. And if you consume L1 data such that you can recompute the state of your L2 using the data that was made available, then you are said to be a rollup. And then there's these 2 more recent concepts. The first one is around sequencing. So if you use L1 sequencing, basically use the L1 validators today, the proposers, to do the ordering of transactions for your L2, you're code-based. And finally, the topic of today's discussion is basically about using the execution layer of the world computer, the EVM, and becoming potentially a native L2 or native rollup. So what I want to do today is basically go through this post from 3 days ago and try and give you a flavor of what is going on, try and tell you about the goals and how those goals could potentially be accomplished. I was hoping that there would be plenty of questions, so please do feel free to ask questions along the way. Okay, so one of the key goals of native rollups is to try and improve the security of rollups, specifically for rollups that are EVM equivalent. So today, we have the full programmability of Ethereum to be able to construct L2s, and in many cases, the programmability allows you to innovate. So, for example, in the case of Starkware, they have Starknet with Cairo, which is like super Snark friendly. In the case of MegaETH, they have this replacement of the state tree, which is 10 times faster to write to, so they have much more throughput. In the case of Aztec, they have this completely new virtual machine, which gives privacy. And in the case of Arbitrum, they have this WASM virtual machine in the context of Stylus, and that's all well and good. But if you just want to do the simplest thing possible in some sense, just be EVM equivalent, then today it's extremely difficult. You have to write your own fraud-proof game. You have to write your own custom circuits. You need to have some security councils. And there's all sorts of ancillary infrastructure for that. You need to have watchtowers in the case of fraud proofs, or you need to have proven networks. And so really what this proposal is here is to make it as simple as possible to deploy an EVM equivalent rollup and to have the exact same security, because when you build this complex infrastructure, you are introducing attack vectors. So for example, if you're building a SNARK circuit to emulate the EVM, more likely than not, you're going to have bugs. Like my my guess is that every single ZKEVM rollup today has critical bugs. And in order to fix those bugs or to mitigate them, we have these security councils, but the security council is in and of itself an attack vector because you're trusting a small committee to potentially just rug you and change the rules under your feet. So the specific proposal of this write-up is to introduce a new execute precompile that takes various inputs. It takes a pre-state root, a post-state root, and a trace. Like those are the three main inputs. There's another one here which I'll discuss later. But these two state roots here are EVM state roots. And you're basically making a claim that if you start with the post-state root here and you execute the trace, so if you start with the pre-state root and you execute the trace, then you will end up with the post-state root. And so really what the trace contains is enough information for anyone to be able to verify that this state transition is correct. And if indeed this state transition is correct, then the precompile will return true. And if it's not, then it will return false. And you can think of the trace as having all the L2 transactions plus the state accesses. So this is a stateless execution. And every time there's a transaction that reads a balance, for example, you need to specify that balance as well as the Merkle path from that balance to the pre-state root. And so the hope is that you can take thousands of lines of code and compress them down to just this one precompile call. And then there's this fourth input, gas used, which is basically there for metering and for pricing. So because this precompile is going to be enforced by the validators, and validators are running on weak devices like a Raspberry Pi, there's only so much they can do, and so there needs to be some gas limits. And even if we use this very fancy way of enforcing the precompile using SNARKs, there will still be a bottleneck, which is on the prover side of things. And so we still need a gas limit, which we have here. So for all of the execute calls that you make in a single block, you take the sum of the usage, and you need to make sure that it's under this gas limit. Now, tomorrow, tomorrow on Friday, the 24th of January, we're going to have sequencing call number 17, and it's going to be an extremely special call with many Rollup founders coming on the call to basically signal their interest and their plans for their Rollup to become native. So if you're interested in native Rollups, do make sure to join that call. If you message me on Telegram with your email address, I can make sure that you're on the calendar invite. And because there's just so much excitement for this precompile in so very little time, we need to think, okay, what is the way to launch it as quickly as possible? And the proposal here is to have an initial phase where the precompile is enforced through naive re-execution. So what does that mean? It means that the validators would be naively re-executing those traces on their full nodes. And the nice thing about the naive re-execution is that it doesn't increase any state, because this is a stateless precompile. It doesn't increase bandwidth, because we're not changing the number of blobs. We're not changing the amount of call data that can be pushed on chain. But the one thing that it does increase is basically CPU cores and execution. So, but the good news is that this execution can be parallelized. So more often than not, when you're running an EVM node, the EVM state transition is run on a single core, because it's a single threaded process. And so here we can make use of the parallelism, which is currently most of the time not used. in Ethereum nodes. And then the more ambitious idea is basically to try and increase the gas limit quite dramatically by having the validators verify SNARKs instead of having to do the naive execution. And here, because there's almost no increase in resource usage from the point of view of the validators, it's okay to have essentially an arbitrary large gas limit from the point of view of the validators. But then there is another bottleneck that comes in, which is the provers. Now, one important thing here is that today, when you build a ZKEVM, more likely than not, there's going to be bugs. And so how do we safely bring the power of zkEVMs to Ethereum L1 without jeopardizing the safety of Ethereum? And one of the key ideas from Vitalik is to actually not have the proofs be enshrined in consensus. So basically, there is no input here, which is proofs or proof. Instead, the key idea is to have the proofs be gossiped off-chain, and for every single validator to choose whatever proof system they're most comfortable with. So for example, what you can do is take Geth and compile it to RISC-V and have SP1 as your backend. So that would be Geth SP1 as your preferred client, or maybe it could be ref with RISC-0. And so you'd have all of these different flavors and combinations of ZKEL clients. And if there's a bug in SP1 but there's no bug in RISC-0, then we're good, because we can just have all of the SP1 validators update, and we'd be left with a network which just keeps on going on so long as we have enough client diversity. Now, one of the requirements in order to have this enforcement by SNARKs is to give the entities doing the proving enough time to generate the proofs. And so there's this notion of real-time proving, which I've been talking about quite a bit. And there's two flavors of real-time proving. There's the same slot real-time proving and next slot real-time proving. Same slot real-time proving is an extremely ambitious thing, because you want to be building your block as close as possible to the deadline so that you have as much fees and MEV as possible. And so you want to be reducing the time that you spend doing the proving. And you might have a budget of 100 milliseconds, or maybe you can push it all the way to 1 second. But even doing proving in 1 second is extremely ambitious. And so the proposal is to have what's known as delayed state roots, where if the Ethereum state root is not put on chain until the next slot. And the advantage for this precompile is that we would have a full 12 seconds to do the proof. And I don't know if you saw the tweet from Succinct today, but they have this SP1 Turbo, which uses a cluster of GPUs, and they can prove blocks in about 30 seconds. And I wouldn't be surprised if sub-slot proving, which is proving within 12 seconds, is a commodity by the end of this year, at least. I hope it is, but even if it's not, certainly in 2026 it should be standard. Let me see if we have any questions so far. Can you please give an example of what is a non-native rollup? So every rollup today is non-native because it's impossible to deploy a native rollup. The definition of a native rollup is one that uses the precompile. And some rollups just fundamentally can't become native just because they've innovated in ways that fundamentally changes the EVM. And so one example of that I mentioned was MegaETH, right? They changed the state tree. Or another example could be Arbitrum, right? They have they exposed the WASM virtual machine within the EVM. And they make a very significant departure from the EVM, and that gives them all sorts of amazing benefits, because now they can have millions of developers who know Rust or JavaScript or whatever that can compile down to WASM. But if you are a rollup that's just trying to be EVM equivalent, then there is a pathway for you to remove your fraud-proof game or remove your SNARK circuit, and instead just use this one line, a precompile, for the state transition specifically. So Hasib is asking, can you share your Telegram handle after the lecture? Yeah, I'm happy to share it now. It's Justin Drake, all lowercase, all one word, if you want to send me your email address. The next question. Did you just say that every single ZK rollup has bugs? Yes. Now, the thing is that these bugs are not being exploited today. And the reason is that we have centralized sequencers. So the centralized sequencers act as gatekeepers for maliciously crafted blocks. So even if there is a critical soundness bug and you can prove arbitrary state roots for a ZK rollup, well, you need the centralized sequencer to be colluding to be the attacker. Otherwise, the centralized sequencer will only propose correctly crafted blocks. But of course, we don't want to have centralized sequencers long term. We want to have permissionless and decentralized sequences where anyone can do the proving. And so at that point, we really, really do need to make sure that all of our bugs are fixed. And the second question is, if yes, at what point do you expect formal methods to address that? So one of the things that I want to highlight is that there's this website, verified zkEVM.org. It's a $20 million formal verification project. So the Ethereum Foundation is putting $20 million that will be spent over 3 years. And there's this guy, Alex Hicks, who joined the Ethereum Foundation recently, and he's the one leading this project. And so if you are a formal verification expert and you want to help with the formal verification of ZK Tech, do make sure to talk with Alex. And one of the things that we're focusing on is ZK RISC-V VMs, and the reason is that there seems to be a convergence towards RISC-V, and formally verifying the correctness of these RISC-V virtual machines is a good first step to get high conviction in these ZKEVMs. What's the EF's approach to solving fragmentation across layers? So there's different types of fragmentation, but one of them, which is, in my opinion, very unfortunate, is this idea of asynchrony. So nowadays we have multiple different rollups, and they each are in an asynchronous silo, meaning that if you want to make a transaction between two of these rollups, it has to happen across multiple slots, and it's going to be done by different proposers, and it's basically an asynchronous call. And from a DevX perspective, this introduces a ton of complication. It's a very strong departure from what we have on L1, which is that if you have a smart contract on L1, it can synchronously call any other L1 smart contract, and that makes things, that basically creates money Legos that are very easy to compose with. And so we've lost this rich composability and this ability to create complex applications across rollups. And the way to address this fragmentation fundamentally is to have shared sequencing. But this is a different topic. This is about sharing the L1 sequencer, for example, when being based. And in my opinion, the way that you solve fragmentation is that we all somehow agree on an Ethereum-wide shared sequencer. But in order for that to happen, the sequencer needs to be maximally credibly neutral. And there's only one sequencer which is maximally credibly neutral, which is Ethereum itself. And the reason is that it doesn't introduce a new brand or a new security assumption or a new token. Now, one thing that I do want to highlight here is that the precompile does help with composability, and the reason is that it's, in addition to get synchronous composability, you actually need two things. You need the real-time proving and the shared sequencing. And what the native Rollup precompile is that it removes the requirement for real-time proving. That is actually done by the L1 as a service. So not only do you not need to worry about the correctness of your circuits, but you also don't need to worry about the performance of your prover. Okay, I think I've addressed all of the questions so far. Now, if you are in the business of building ZKVMs or ZKEVMs, or if you're in the business of trying to accelerate provers, one of the goals, I guess, that I would encourage you to try and reach is this notion of next lot real-time proving, where the proof latency is under 12 seconds. And actually, to make it even harder, I'd say it's 12 seconds minus the time it takes to gossip these proofs. Let's say that's 1 second. So really, what we should be aiming for is about 11 seconds of latency. Okay, so one reason, let's discuss some of the benefits for having these off-chain proofs. So the first one that I mentioned is that it gives every validator the option to choose the verifier. So if there's a bug in one of them, it doesn't take down all of Ethereum. But another big benefit is that it means that the L1 doesn't need to pick a specific winner. We don't need to pick Plonky3 as a winner or Risk0 as a winner. Instead, it's an open market, and just let the winners naturally evolve. A third benefit is simplicity, meaning that we don't need to enshrine in consensus a specific verifier. Instead, we can we just need to specify the high-level API of this precompile, the inputs and outputs. And then finally, there's this great flexibility where if there is a bug that's found, well, the validators can update their clients without needing a hard fork. Just like today, if there's a bug in ref, then the validators can just update their clients. Okay, so it's a little difficult because I can't see anyone and I can't hear anyone. But I'll have a quick look at some of the questions. Are single slot proving and encrypted mempool somewhat related or independent concepts? They're completely independent. So, encrypted mempools is about privacy, and confusingly, we use the term ZKVM or ZKEVM, somewhat as an abuse of the term ZK. That when we talk about ZKVMs or ZKVMs, there is no notion of privacy. Anna Rose has this great term where she talks about the royal we, right? So we've abused the term ZK to basically mean fancy cryptography that is useful in the context of blockchains, or more specifically SNARKs. I haven't followed SP1 Turbo that much, but what is stopping them from having proving done in under 12 seconds by throwing more compute? What's the bottleneck there to get time under target? So right now, I know that one of the bottlenecks, ironically, is not the proving, but it's the RISC-V execution. So I believe that they can run RISC-V at roughly 50 megahertz, which is comparatively slow to native execution on the CPU. And so yeah, there's all sorts of tricks where you can try and add checkpoints and then parallelize the execution of RISC-V. But I think it's just a matter of engineering to make sure that that everything gets parallelized. what is the role of pre-confirmation, and is it going to solve real-time proving issues? Okay, so pre-confirmations are about the sequencing layer, not about the execution layer. So these are completely independent layers of the stack, as I tried to highlight here. So the based sequencer is amazing. It's maximally secure, maximally neutral. It has maximum sensitive resistance, but it has one massive downside, which is the slot duration of 12 seconds. And so what pre-confirmations are trying to do is basically trying to make the next proposer give promises about what they will include in their next block. So from a UX standpoint, you get cryptoeconomic guarantees that your transactions will execute in a certain way without your transaction actually being included in a block. So for example, let's say you want to make a trade on Uniswap. You tell the next proposer, hey, I want to make a trade on Uniswap. The next proposer will say, yes, that's fine. This is how your trade will execute. So you know exactly what is your execution price and what are your fees. And then it returns a promise saying, if I don't include your transaction as I promised, then you can go ahead and slash me. So the next sequencer will basically have some amount of collateral to back the promises. And then there's a slashing mechanism in case the proposer does not indeed create a block as they promised. And so we're basically abstracting the slot duration from the point of view of UX. There is no slot. They don't even know there's a slot. It's just ping latency, right? The time it takes for the pre-confirmation request to reach the sequencer and back. So it's one ping of latency, and maybe just a few milliseconds for the sequencer to actually craft their promise, which is just a signed message. This means that MEV in the context of SNARKs is impossible. So one of the things that I mentioned here is this notion of MEV driven proof racing. So if we didn't have this next lot delayed state roots, we'd be in a position where the fastest provers would have an edge over the slowest provers, because they'd be able to generate the proofs in a small amount of time and collect more MEV. And so that is a kind of a centralization vector where the most performant prover gets to collect the most MEV, and then they become even more performant and collect even more MEV. And so instead, by delaying the state root by one slot and giving everyone a whole slot to do the proving, well, that's a fair playing ground, and everyone should be able to do the proving within the whole slot. Okay, so now let me talk about some of the challenges with this design, where the proofs are gossiped off-chain. One of them is that there's more prover load, and the reason is that for every zkEL client, by the way, EL means execution layer. So for GEF, for REF, for BESU, you would need at least one proof for each of these clients. And not only that, every time there's a version bump on the client, that is a new proof, because you have new circuits or new RISC-V bytecode or some other bytecode. And then on top of that, for every high-level execution client can be compiled to different ZKEVM. So there's potentially a quadratic blow-up here so you have K different ELs, L different ZKEVMs, and so there's a K times L different combinations. And so in order to somehow have a reasonable number of proofs that need to be generated, like my suggestion is that every single EL picks a canonical ZKEVM. And in order to do that in a graceful way, you can actually pair the very fast ELs with the slower ZKEVMs and vice versa. You can pair the fast ZKEVMs with the slow ELs. So, you know, if for example, I don't know, ref is considered to be extremely fast as an EL, well, you can pair it with a slow ZKEVM. I don't know. And you know, if SP1, for example, is considered to be extremely fast, well, then you can pair it with a slow EL. So that would reduce a lot of the blow up there, and it would allow everyone to generate proofs in a reasonable amount of time. And then another problem here is this idea of minority ELs. So today on Ethereum, if you go to clientdiversity.org, you'll see that you know, there's some very popular ELs like Geth and Nevermind, and then there's some that are not so popular like Aragon. And so you'd think that as an execution proposer that needs to generate these proofs, I'm not going to bother generating proofs for Aragon because it's only going to give me 3% of attestations, and I don't need that last few percentage of attesters in order to get my slot on chain. So it might be sufficient to only generate you know, Geth and Nevermind proofs, and then I'm kind of done. Well, one way to address this is to basically have every validator run every single client. And this is something that's not possible today because, you know, if every client consumes 2 terabytes, then you need 10 terabytes. And, you know, the institutional validators will do that. So there's this thing called Vouch, which is basically a multi-client architecture, which allows validators to run multiple clients in parallel, for example, 5 of them. And if at least 3 or 4, for example, agree, then that counts as the truth. And this is, everyone can basically run a vouch-like setup in the context of SNARKs because you don't need to run these expensive full nodes. Instead, you have ZK full nodes, which are extremely, extremely cheap. And so there wouldn't be a notion of minority clients. Every client would be a majority client. And that helps address the issue a little bit. Now, one question that you might be asking is about this gas limit. Isn't this gas limit like really a limitation, because it means that all the rollups need to be limited by this one master gas limit? Well, one piece of good news here is that the optimistic rollups won't be consuming this gas limit. And the reason is that they only have to call the execute precompile in a challenge game. So by default, what they do is that they just build their optimistic rollup by pushing the L2 blocks and making claims about the state root. And only if there is a disagreement about the state root do they use the execute precompile to resolve the disagreement. So it's you know, you just need the execute precompile as a way to disincentivize the creation of raw proof. But if you're dealing with rational actors, then that precompile should never be called. And so you can have native optimistic rollups that essentially have unlimited gas limit. It could be, you know, a gigagas, teragas. Really the bottleneck will not be the L1, at least not the L1 execution. You said that ref is popular and fast, but only takes 2%. So I did say that ref is fast, and it is indeed very popular within the MEV pipeline. So ref is used, you know, by essentially all of the builders, all of the searchers. Is basically, and the reason is that they're interested in ultra low latency block building and bundle building. But ref is is a last mover in some sense. It's a very recent client, and it only moved away from its alpha status quite recently, and so it's only those that are willing to live on the bleeding edge that are running Ref. But I do expect the popularity of Ref with the validators to grow quite significantly in 2025 and 2026. This slide says enforcement by SNARKs. When do we get the opcode to enable that on mainnet? Okay, so my hope is that we can have the opcode in 2026. And the reason is that we don't need the delayed state root. We don't need the fancy SNARKs. And we also don't need what's called attester proposer separation, or APS, which is one of the dependencies to have the SNARK enforcement. So hopefully, in 2026, we have this precompile. And then if we want to enable the enforcement by SNARKs, we can start raising the gas limit without a hard fork, right? Because one by one, some of the validators can basically update their setup to start verifying with SNARKs. And once the community, the social layer, believes that it's safe to start increasing the gas limit, because most of the weak validators are verifying the execute precompiled using SNARKs, then we can just all vote to increase the gas limit. By the way, on that note, if you are a validator, please consider voting to increase the gas limit. So the gas limit is actually controlled by the stakers. And if you click on show individual entities here, you will see various entities that have already started voting to increase the gas limit. So it's currently at 30 million gas, and I think there is rough consensus from the devs that 36 million gas is indeed safe. And once we have enforcement by SNARKs, my belief is that we can increase the gas limit by orders of magnitude, like 10x, 100x. And the reason is that, again, the validators will just be verifying SNARKs. And today, the meme is that validators should be able to run on a Raspberry Pi. I think once we have SNARKs, the meme should be that validators can run on smartwatches. And so we have this extremely low barrier to entry from a computational standpoint to become a validator. And then the second, well, maybe the largest other barrier to entry to become a validator today is to have 32 ETH, which is about $100,000. And hopefully that will go down to 1 ETH at some point. And then maybe the final barrier to entry today in terms of sophistication to be a validator is to be exposed to the MEV pipeline. So today as a validator, you get to pick a relay, and you need to play timing games in order to be maximally efficient. And when you do win a block, you get what's called an MEV spike, which creates a lot of variance in your staking returns. And unfortunately, the median validator makes less than the average validator. And the reason is that, sometimes there's a jackpot winner. There's someone that made hundreds of ETH because they happened to build a block when there was a lot of MEV. And the one jackpot winner makes a ton of APR, but the median validator will lose. And so the fact that you need to smooth MEV is one of the incentives to be sophisticated, and that's something that should go away with attester proposer separation. What is a good project to build if we want to work on native rollups? Okay, so you can build anything on top of a native rollup. You can build a DEX. You can build, Aave can be a native. Aave chain can be a native rollup. ENS chain, which is called name chain, could be a native rollup. You can also you can basically any EVM equivalent chain could be a native rollup. And actually, one of the speakers, so tomorrow we're going to have about 20 different speakers. And one of the speakers will be Vitalik, and he will talk about his vision of using base and native rollups to fund public goods. So yeah, stay tuned for that. How would the transition from non-native rollups to such proposed native rollup take place, and what does it look like? So basically what needs to happen is that the EVM equivalent rollups need to isolate their state transition function, whether that's in the foolproof game or in the SNARK circuit, and basically take all of that logic, ditch it, and replace it with one precompile. So they would need to use their governance powers, whether that's a security council or a token governance, in order to swap out their logic and update their smart contract. But yeah, the whole point is that eventually they can completely remove their security council, completely remove their token governance, control over the virtual machine, and basically fully inherit L1 security. And if you fully inherit L1 security, I call such rollups trustless rollups, or you could say the World War III grade rollups. And I'm hoping that this will lead to a lot of money flowing into the rollups, because today the big money, institutions or whatever it is, I don't think they're comfortable, putting hundreds of billions of dollars or trillions of dollars on these rollups, precisely because of the security concerns. And so once we have both scalability and security, we can hope to have trillions of dollars on these rollups. Are we going towards a world where non-native rollups will be forced to move towards native rollups, or will they both coexist indefinitely? So there's definitely no forcing going on. So any move to a native rollup is a voluntary process. It's an opt-in process. And I definitely do expect many rollups will not want to be native. And the reason is that there's some sort of significant departure from the EVM that justifies their departure. This is something that I mentioned at the beginning of the call. There could be some rollups that are, for example, SVM rollups. There's Eclipse or Ellipsis. Those are both SVM, so the Solana virtual machine validiums, and they get some sort of like performance and throughput benefit. So my understanding is that today actually Eclipse has 3,000 TPS. It's a validium, and it'll be difficult for that to be achieved with the EVM. Now, one small note that I actually didn't mention in the write-up is that an advantage of native rollups is that they're post-quantum secure. And the reason is that there's no proof that goes on chain that is post-quantum insecure. And if for whatever, even if post-quantum insecure proofs are submitted off-chain, well, those can just be upgraded without a hard fork to become post-quantum secure. So today, the way that rollups generally settle, almost all rollups do that, is that they will wrap the proofs inside some sort of a small gas efficient proofs, like a Groth 16 or a Planck proof, and that means that they can only consume a few 100,000 gas to settle, but that comes at the downside of not being post-quantum secure. So if they wanted to make their proving like completely immutable, well, that's not a very good strategy, because 1 or 2 decades in the future, the rollup would break because of quantum computers. And so, the whole point of blockchains is to build infrastructure that will live centuries, and being a native rollup is one way to get that long-term post-quantum security. Hey, Justin. To learn more about this topic on rollups and infrastructure, do you have any recommendation related to ZK and post-quantum technology? So there's actually a quantum episode that came out recently on Bankless, which I thought was quite interesting. And related to ZK, one website that I want to show here is EVProofs.org. So it hasn't been announced just yet. There's a preview. So if you click on check out the preview, what it does, it's basically a website to showcase the various ZKEVM vendors and provers. And for each, so basically we're trying to incentivize proofs for mainnet blocks. So the way we do it today is that we encourage proofs for blocks that end in 00, so 88400, 88300, etc., etc. And you can see here that there's 2 blocks that have been already published, and then there's one that is in flight. So there's 3 different provers right now. There's SP1, ZKEVM, and SNARKify. And so let's have a look, for example, at this block here. Actually, you know what? Let's go with this one. So yeah, here you can see the SNARKify, ZKEVM, and succinct. And we're still waiting on succinct. But SNARKify, it took 13 minutes for the proof to arrive, ZKEVM 12 minutes. And this is the cost of the proof. You can go download the proof. Yeah, it tells you how many ZKEVM cycles that they used. And the way that we calculate the proof is, there you go, is by having them disclose the AWS equivalent machine that they use. So and in the case of SNARKify, they used basically a P2X large with 4 virtual CPUs and a bunch of memory. And this is how much it costs per hour, $0.9. And because it only took them 6 minutes of proving time, it only cost them 9 cents to generate the proof. Now, if you are interested in being on this website because you're a prover or ZKEVM vendor, do get in touch with me on Telegram. I'm Justin Drake, all lowercase, all one word, and I can put you in touch with the EVProofs.org. And basically what we want to do is create this equivalent of L2 beat for ZKEVM provers. And we really want to highlight the leaderboards on proving time and cost and all of these things. And ideally, we get to a point where there's healthy competition and we all converge towards this sub-slot real-time proving. Okay, what technique properties are those proofs make them post-quantum secure? So in the context of native rollups, really what gives us the post-quantum security is the flexibility to change when relevant to post-quantum secure SNARKs. We know how to build post-quantum secure SNARKs, using hashes. And there's techniques like Fry, which are very standard nowadays and actually used in practice quite a bit because they also have very fast provers. The downside of these hash-based proofs is that they're very large, and so you need this. Well, a lot of people opt to use wrapper SNARKs that make them smaller to be ingested on chain. Okay, I mean, I think that's pretty much it. If there are more questions, happy to answer them. If you're interested in learning more about interest in native rollups, do come to tomorrow's call. There should be, 10 or so different rollup founders that will discuss the topic.
Thank you so much, Justin. Everybody, thank you for participating in the workshop. If you have any last question, now is the time to post them. We still have a few minutes. For those that are asking about recordings and everything else, we will make sure to make these available in the next 24 hours. They will be added to the Hacker Pack, a link to which I'm sharing in chat. Once again, you will have a list of the previous recordings as well as this one in the document that's been shared.
So we do have one question that came up. For the future vision of validators running ZK proofs on smartwatches, if I understood correctly, what do the proving specs look like for the proving systems in such a world, and how decentralized will they be? Okay, so on the verification side of things, on the validator side of things, everything is snarkified. So you need no state and no compute. And then for the bandwidth, you're using what's called data availability sampling, which is a way to know that the data is available without actually downloading the data. So your bandwidth is minimal. Now, the question then becomes, on the prover side of things, what are the kind of machines that we're expecting to be using? And I have a sentence here basically talking about this. So if we want to be super conservative on the gas limit, then we can make the proving be accessible to laptops. And the reason why we want accessibility here is in the case that the execution proposers don't do the proving, there needs to be some sort of a fallback mechanism that is much more accessible to anyone. So one possible answer is just to target laptops, for example, high-end MacBook Pros. I think a more pragmatic and aggressive strategy would be to target a small cluster of GPUs. So I believe that the succinct, turbo numbers come from, a cluster of GPUs, maybe on the order of 100 GPUs. 100 GPUs, sounds quite high. I don't know, maybe a smaller number of GPUs is acceptable. But the important thing here is that we only need one person in the world to do this. So it's, technically speaking, it's an honest minority assumption or an altruistic minority assumption. And those in general are very easy to get, or at least much, much, much easier to get than the honest majority. So consensus is based on honest majority, where you need n/2 out of n to be honest, which is extremely hard to get. Whereas honest minority is just, you need one person in the whole world, 1 of n, in order for this whole thing to work. But what I'm hoping will happen over the next few years is that we're going to have SNARK proving ASICs. And so I think there is a world where we can manufacture thousands of those prover boxes and have them widely distributed among the Ethereum community. And surely one of these thousands of boxes will be, connected to power and to the internet and can do the proving. And at that point, we can have really, really high execute gas limit. Okay, final question. Could you tell us more about the Beam chain? So the Beam chain is this very ambitious long-term upgrade to the Beacon chain, and we're trying to have all of the latest and greatest research ideas be pushed in one go on this this big upgrade. Anything that cannot be done incrementally through an incremental fork to the Beacon chain would basically go in the Beam chain. And it's still very early days in the sense that we don't have a Beam spec. So the spec is the plan is to have it in 2025, by the end of 2025, and then the real building, the engineering, would happen in 2026 and 2027. But what's happening today is basically at the social layer, we have teams that are starting to form and express interest in building a Beam client. So we have the existing 6 consensus layer teams that have expressed an interest in building a Beam client. And in addition to that, we have eight new teams that have formed to build a or that have expressed an interest in building Beam clients. So in total, we have 14 different teams. My hope is to basically support these teams with grants, with a Beam call. So the idea is to have a monthly Beam call where we talk about the latest research. There's going to be Beam days this year around some big conferences like EVCC and DevConnect. And we might even have a Beam retreat over a whole week or several days where people can spend lots of time in person to discuss this ambitious project. But yeah, overall, right now we have about 100 developers spread across 14 teams that are interested in building the Beam clients.
All right. Thank you so much. Everybody, I've also shared a quick link from the ETH research link that Justin's been sharing throughout the session. It's in the chat. We will also make it available within HackerPack tomorrow. So yeah, that's all. Thank you for coming today. This was, as I said, just the very first workshop of today. We're going to be having a second one we're hosted by Abhishek from Google. It's going to be happening in 2 hours. So see you all back then. Thanks so much again, Justin, for this workshop, amazing lecture, and we'll follow up afterwards. Thank you so much. Have a great day, everybody, and see you soon.
Thank you.